All right, so looking ahead to the rest of the semester, okay? We're going to do exponentials and logs for the next few days, and it's going to be a flipped model, okay? So we're going to start by watching the first video in class today, okay? Then after this, I expect you to watch the video before you get to the next class, okay? So, like for instance, today we're going to do 9.1 in class. We're going to then do, I'm going to expect you to have watched the 9.2 video before you get to class on Thursday, okay? Because then Thursday, I'm going to use it as application type time in class to go over this stuff, make sure that you guys understand it, answer questions, all that good stuff. Okay? What you need to do is you need to go on top of the packet that I handed out to you. Actually, let me, before I even start about that. So this is going to take us up until, I believe it is next week, Thursday. Correction, next week, Friday. Okay? So next week, Friday is going to be your exponential and log test. Okay? On Friday. That leaves Monday to review for the final. And then Tuesday is conflict resolution day. And then your final is going to be on day 2, period 1. So that's Thursday the 19th, period 1, in room 317 to 319. Everybody's going to be together in one room taking the final at one time. Okay? Day 2, period 1, room 317. Okay? And we'll talk more about that as we get closer to it, but that is official now. You'll actually get that tomorrow in homework for you. Okay? So, and then remember that your semester 1 final is actually going to be part of the NTC final. Okay? So I'm just going to pull out the questions that I'm going to pull out an hour's worth of questions, kind of deal of stuff that we've gone over, and then you'll take that first semester. It will go in as part 1 of your final that you will take part 2 of at the end of the second semester. I'm also you guys are the guinea pig. Yeah. We're piloting it. You're my guinea pigs. So yeah, I think it'll work out for everybody. So, okay. Now that packet that I gave you, that's the notes packet that you are going to want to have for this entire unit. Okay, that's your notes. You're going to want that especially when you're watching the videos. So today you're going to have it in class. Tonight or tomorrow night or both nights, whenever it is you decide to watch the video for it, okay, then you're going to want to use that packet to go along with. Now, one thing I can tell you is this, okay? At the top of that packet, I want you to write down this website. I don't know why I switched to lowercase letters. I don't like lowercase letters. Okay. The website is algebra2.flipmath.com. Okay. Let's go there. Okay. When you're there at algebra2.flipmath.com, okay, then you're going to want to go into semester 2. And then in semester 2, you're going to want to we can call it units. Okay? Then you're going to want to go into unit number 9. Okay? When you do that, that will take you to a page. Well, so then you've got the different ones to do. Okay? So right now, today, we're going to do 9.1. Okay? Now, that will take you to a couple of different things. If I scroll down here, first off, it will give you the lesson objectives. Don't worry about those. Okay? Then it's going to have a video, and then it's got a bunch of stuff after that too. So it's got the packet for 9.1. You already have that. That's what you have in your hands right now. Okay? Is the packet. Practice solutions. Okay? So that's basically the filled-in version of the packet. Okay? Which you'll fill in as you go along. It's got 2 different corrective assignments. Okay? One of them you will get a day, and I vary which one that you'll get every day, but you'll get those every class period for homework. Okay? And then it's also got, if you want to download the video, you can download the video. Okay? But you can just play it right through that. Okay? Then it's also got an application walkthrough, okay, with some SAT prep questions, but we're ACT, so don't worry about that. Okay? But when you're watching the video, if you, up here in the corner, if you click on it, if you click up in the upper right-hand corner, it'll pop it into a full screen. You can watch it in the small screen, but yeah, it'll pop it in. Well, the videos are vary in length. Some of them are 20 minutes long. I think today is like 18 minutes. Okay? Some of them are 10. Okay? Very easy. You can pause them as you're going along to fill in or do a graph, or if it's a different teacher. Okay? It's not me. It's a different teacher. So he's got different jokes. He's got different other teachers in their department. You know, kind of a deal. But you know, just work through all that. Pause it if you need to. So on and so forth. Okay. So today we're going to watch this video. Okay. Right. And then you're going to answer some questions on there as we're going along. If you need me to pause it, I can pause it.
Hello and welcome to a fun and exciting lesson on exponential growth. My name is Mr. Bean, and we're going to start off this lesson with a little story. Once upon a time, there was a beautiful princess named Kellerina. Okay, maybe not so beautiful. This princess had been kidnapped by an evil dragon named Dragon Brush. Maybe not so. Kellerina's father was the king, King Von Sully. King Von Sully offered a very considerable sum of money to anyone in the kingdom that could rescue his daughter from the evil dragon. There was one such brave hero in the kingdom willing to risk life and limb, Signor Beano, who was, not that Beano. There we go, that's Signor Beano. Signor Beano told the king that he would rescue his not-so-beautiful daughter from the not-so-evil dragon. King Von Sully at first offered $1 million to anyone who could rescue his daughter.
$1 million.
But King Von Sully realized $1 million probably wasn't enough, considering he was the king and all, and he was very wealthy. So instead, he offered Signor Beano $1 trillion. That's the same as having 1 million millionaires offer all of their money. Now, Signor Beano went to the king and said, "Sire, I don't want to take advantage of your generosity, so being the good person that I am, I have another idea for my payment. If you'll take a chessboard and put 1 penny on the first square, and then double that and put 2 pennies on the second square, and then double it again and put 4 pennies on the third square, and continue that doubling process until you fill up the entire board. After only 1 line, the king saw that the total amount of money was only a little over $2. He was so impressed with Signor Beano's magnanimous offer, he immediately accepted this agreement. In today's lesson, you will see how much money Signor Beano will actually receive after the entire chessboard is filled up. This process of doubling is an example of something called exponential growth. And while it may not seem like
So, just to clarify, this is $1.28 is not over $2. Okay? But all told, so this would be the first day he gave a penny. Second day he got 2 pennies. Third day he got 4 pennies. If you add all those up, it's just over $2. What even is it? 1, 3, 7, 15, 31, 63, 127, 220, no, 255. $2.55. Okay? Okay?
much at first, you will see how rapidly it increases, and that Senor Pino is not nearly as nice as he appears. So let's get into the bulk of the lesson now, dealing with exponential growth functions. If the variable is not in the exponent, then it is not an exponential function. Here's what that means. We look here at the exponent. Here we have an x up there in the exponent, and that is the variable, and therefore it is an exponential function. It must be in the exponent.
Remember, I know it's the variable because the function is being defined as that. If this were f of t, and I gave you that, it would not be exponential. Okay? Because the variable is being defined as the variable I'm using is x, therefore that it makes it exponential.
Now let me put this another way. Here's how I remember this. It's funny. Ready? We have the word exponent. And if you take the x out of the exponent, you get exponent. Exponential function. There's no such thing as exponential function. It's got to be an exponential function. Get it? Okay? Or there's really no such thing as exponential function. Please don't say that in the future. That's embarrassing. All right, so here you have, writing this down in our notes, what we call the initial value, what you're starting off with. And then B here, the base, is a growth or decay factor. Now, for today's lesson, we're focusing just on growth factors. Next lesson, we'll do both growth and decay. This will also set up for when we start doing model, real-world application stuff. We'll do a lot more of that in the next lesson. A couple conditions with this is that A cannot be 0. If this was a 0, then the whole thing would become 0, and you would just get y equals 0. Okay, that would be kind of dumb, so we're not doing that. A cannot be a 0, the initial value. Also, the condition 2 is the base must be positive, and it cannot be 1. So it's got to be some positive number, and we can't be the number 1. If it was the number 1, then 1 to the x would just equal 1, and it would just be a times 1 all over the place. So those are the two conditions for exponential functions. So let's identify whether or not these are exponential or not. So for the first one, 2 raised to the x, is this exponential? Yes, it is. And the initial value is, this is tricky, it's a 1, and the base is a 2. See, this is a base 2, and there's a, you don't see it, but there's a 1 times in front of this thing, so a is a 1. Is number 2 here, is this one exponential? This one is not, and it is not exponential because, we're going to get rid of those lines, because the variable is not in the exponent. Remember, exponential, it's got to be inside exponential, exponent. All right, here we have the variable up here in the exponent, that's okay. The base is positive. The number can be negative in front, that's okay, so this one is yes. A is negative 3, the initial value is negative 3, and the growth factor is a 2.6. This one here, is it exponential? It is. You might have wanted to say, no, it's not, but here's why. The A is a 10, and the base, this is a little tricky, you're not good, if you remember this, this is the same thing, I'm going to write it down here, this is the same thing as 1/6 raised to the x power. A negative exponent means you flip it, and so the base is actually 1/6, not just a 6. And then here, this is tricky here too, we're going to get into this in 9.3, 9.4, E is not a variable, and so this is not exponential. In fact, there are no exponents anywhere in this. E represents a number, kind of like pi is a number, E is its own special number. We'll do that later in this unit. Linear versus exponential. Here you have an equation. I want you to write down the equations for these. I wrote those in for you, but they look very similar.
So write down those equations and those racks. Give you a couple of seconds to do that.
First you have 2 times x, and the second one you have 2 raised to the x. So please be careful when you're writing it on your pieces of paper and on your homework practice and all that stuff, that when you have to write 2 raised to the x, that you make it obvious it's 2 raised to the x. Don't write something like this that kind of hard to tell. Okay, is that 2x, 2 raised to the x? Make it obvious when you're writing these things down. And there's the difference.
Because it does make a difference, okay, where it is. If the x is down below, okay, not in the exponent, it's a line. It's linear, okay? If it's in the exponent, then it becomes an exponential type equation, and as you can see, those are not the same. Yeah?
Of the graph as well. Just a straight line versus a curved line that looks exponential. Okay, a few things right down here about the exponential growth functions. One is that if the b value is greater than 1, if b is larger than 1, then it is going to grow away from what we call the asymptote as you move left to right. Okay, well, what in the world is an asymptote? It says here in this paragraph, you want to copy that down, but put this, it's hard to see on here, but I'm going to put a dashed line right on the x-axis.
You already know what asymptote.
Right along the x-axis. This is some imaginary line. You don't see it, but it is going to be a line that the graph is going to approach closer and closer to. Okay, we will talk a lot more about these in the next unit, Unit 10, with Mr. Brust. He'll cover this stuff. But as you move left to right, remember, you're going this way. As you move left to right, the graph is going to be growing away from it if b is greater than 1. And what is the domain? The domain is all real numbers. As you move left to right, all of the x's on there on this graph, it goes forever. Another way of saying all real numbers, nice little shortcut. So you put two lines like this, and you make an R. This represents all real numbers. You have to write out the word all real numbers every single time. The range is the y values of this graph, and all the y values are y is greater than 0. Now, what are these dots here for? We'll come back to that later in this lesson.
Okay, so domain we've talked about before. Okay, range now, range is the output. It's what values the function can give you. So what this is saying, when you say that the range is y is greater than 0, that's saying then that the function can never cross the x-axis and it can never go negative. No matter what value you put into this function, it's never going to give you a negative value. Yeah. Range is always y, domain is always x's. Yep. Yep.
Lesson, I just want you to have it on here, so remember we will come back to this. Now we have growth versus decay. So this is our lesson here. We're doing this one today, and our next lesson we'll do decay. So if you're moving left to right, it's going to grow away. Another thing that it could do is if you had a graph that was doing something like this, that would also be growth. Because moving left to right is going away. There's decay. Left to right is getting closer, or you could have something like this. As you move left to right, it'd be getting closer. But this is our focus today, growth. So for these graphs, which ones are growth functions? This one, as you move left to right, it's getting, actually, I'm not telling you, pause it, and then I'll.
Okay. So, which ones are growth, which ones are decay? Okay? Okay, growth or decay?
Well, it's going away from your horizontal asymptote, it's going away, so it's growth.
Okay, ready?
I'll have the answers there. All right, I tried to have the answers here pop up for you, and the first one was the decay, growth, and decay. So just remember moving left to right, whether it's growing away from it or decaying closer to the asymptote. Let's create our first graph of the exponential.
There we go. Right?
Actually, I'm not telling you, pause it, and then I'll have the answers here.
Pause it, and
All right, I tried to have the answers.
okay. Any questions on those? Why those are growths and why those are decays? If it's getting closer to the asymptote on the right side, it's decay. If it's going away from the asymptote on the right side, it's growth. Okay? Good? Asymptote always going to be horizontal.
Yeah, it's where the line is, where the line's kind of straight down.
Yeah,
That's what
because it's gonna flatten out. Okay. Yeah.
Here pop up for you, and the first one was a decay, growth, growth, and decay. So just remember moving left to right, whether it's growing away from it or decaying closer to the asymptote. Let's create our first graph of these exponential functions, and what we'll do is we're going to plug in some test points. We'll do a little P-chart. I'll plug in the number 0, a 1, and a 2. In fact, I'll even go up to 3. Let's see what we get. If you plug it,
Now, rule of thumb, standard rule of thumb is you want your exponent to be equal to 0, and you want your exponent to be equal to 1. And then branch out from there. Okay? But you definitely want your exponents to be 0 and exponents to be 1. So you look at the exponent and you set it equal to 0, do a quick mental solve on that one. That tells you what x value you can put in. Okay? He's going to teach you the transformation method in a little bit, but either way, you can just do the quick mental math of getting that exponent equal to 0 and exponent equal to 1, and then branch out from there.
get a 0 here. So just maybe do some side work, maybe in the margins if you're not enough room. So we'll have 1/2 times 2 raised to the 0 power. Well, what's 2 to the 0 power? That's 1. So we just have 1/2 times 1. So the y value is 1/2. Right now let's do the number 1. Now we have 1/2 times 2 raised to the first power. That's 1/2 times 2, which equals 1. So when x is 1, the y value is 1. All right, now do this again. We plug in the number 2 into the x value. So plug in a 2 there. We get 1/2 times 4, and half of 4 is a 2. Next one. We have
Now, I can tell you this. Mental math is going to be a lot quicker for you and a lot less mistake prone than doing it on a calculator. Okay? You can use a calculator, but it has to be a non-graphing calculator for this unit. Okay? Right? So just know that mentally it's going to be quicker for you to do this stuff, and that's why we choose stuff close to 1 and get the exponents to 1 and exponents to 0. Okay? An exponent of 0 produces that whole term as 1. Okay? So anything to the 0 power is 1. And that's why we want that exponent to be 0. Because that term then becomes 1. Okay? And if I take x to the first power, then that's just going to be x. Okay? So if it's 4 to the first power, it's just 4. Okay? You get farther and farther out, away from there, either the ginormous numbers they become, or the smaller numbers that they become, minuscule. Okay? Because if I went 4 squared, that's 16. Tough to graph 16 on a graph that only got 10 spaces on it, without doing any of the other things. Okay? Alright? So just know that the farther out you go,
1/2 times 2 raised to the third power. And let's see here, that means 1/2 times 2 to the third is 8. Not 6, it's 8. And then half of 8 is a 4. All right, so now we have some values that we can plug into this graph. So we go 0, 1/2, and let's switch colors. There we go, a little bit easier to see. 0, 1/2, 1, 1, 2 and 2, 1, 2, 3, 3 and 4. Okay, and now we can see, we could keep getting some more points, and we have our asymptote is going to be, this is what the graph looks like. going to be very, very close to this thing, and I'm drawing this freehand here, so it's going to be really squiggly. I'm trying not to make it squiggly. And then you start growing up like this, and it grows really fast as you move left to right. That is what this graph looks like. What is the domain? We have all real numbers, all of the x values, left to right, forever and ever. And then the ranges are all of the y values that are larger than the asymptote. And the asymptote in this case is the x-axis. If y equals 0 is the x-axis. And so if it's above that line, we put y is greater than 0. All right, first one down. So now this box would work, these coordinate points will work for every exponential function that we're trying to plug in, unless things are shifted and translated, which will show how to deal with that. So if you plug in a 0 here, remember, this becomes a 0, then b to 0 is 1, and all you're left with is a. That's going to happen every time. So 0, comma a is a quick coordinate point. You're not having to do a lot of calculations. Same with this first, with the number 1. If you plug in a 1, it's just a times b. So there's another quick and easy coordinate point. Those are two fast, easy coordinate points, along with sketching the asymptote, that can help us sketch these graphs. You know, if we wanted to add another one to this, 2 comma a b squared, that might be another one that could be fast. So these would be, we always want to do at least 2 points, preferably 3, to help us sketch this stuff. 3 is best to have if it fits on the graph. Now before we go on to the next part of this lesson, I've got to make sure I emphasize you are not going to be allowed to use a calculator on this mastery check. And so for the practice and for the rest of the notes, you want to try and do everything you can without needing to refer to a graphing calculator. That brings us to this. Well, what are these 3 points here? This first one here, that one would be 0, comma, a. So go back in your notes and let's add this in. And then this coordinate point here would be 1, comma, a times b. And then this coordinate point would be 2, comma, a times b squared. Those are 3 coordinate points along with the asymptote that can help you sketch it. Now we will graph number 2. I'm going to do this number 2 with you, and I'll let you try number 3 on your own. So again, we are going to look at coordinate points 0, comma, 1/2. Remember 0, comma a, that first one. And then 1, comma, if we plug in a 1, it's just going to be 1/2 times 3. Half of 3 is 1.5. You could say 3 halves, leave it as a fraction, or 1.5. I like decimals when I'm putting things on a graph, just because it's so easier. And then if I did a 2, let's do one more so we can get another coordinate point. So 3 squared is 9, and then half of 9 is 4.5. So let's graph them. I read.
Everybody see how we got those? Okay. He plugged in 1, plugged in 0 in his mind. Okay. So 3 to the 0 gets me 1. 1 times 1/2 is 1/2. Plug in 1. 3 to the first is 3, times 2 is 3 halves, which is 1.5. 2. 3 squared times 1/2 is 4.5.
0 and a half. 1 and 1.5. And then 2 and 1, 2, 3, 4 and a half. Okay, so there's our coordinate points. We have our asymptote over here on the left. It's really close to the x-axis. And then, much better. Oh, spoke too fast. Let's say that was nice and smooth. So it almost looks like a straight line on the left, and then it starts to curve up, and hopefully yours looks better than mine. All right, there's our graph. What is the domain? I'll put arrows on the end here. It goes forever. The domain is all real numbers. It's going on forever. And the range will be all of the y values that are greater than 0. All right, done. Let's try number 3. Before we start it, I'll at least give you this hint. What does a equal and what does b equal? A is equal to -1, and b is the base, b is a 2. So start with that, see if you can graph this one. I'll have the answer if you're here.
Okay. So graph that one.
We get the one that's due for tomorrow done. Can we go on then and keep going farther into it, or do you want us to just go through it?
Day by day.
Just I think on the light for a little moment.
And there's your answer to number 3. I plugged in a few different points, not just the 3, but the 3, -8, just to give you an idea where it would be on this graph. This time, because it was negative in front, it's below the x-axis. The domain's all real numbers. And then be careful here, the range was now y is less than 0, because we're underneath the asymptote.
Questions on that one? Okay. Notice how the negative sign is not inside the parentheses. Okay? Please excuse my dear Aunt Sally says we do the exponent first. So if I'm looking at, to get this 2 here, or to get 2 comma negative 4, when I put 2 into the function, that's 2 squared, which is 4, times negative 1 gives me the negative 4. Okay? It's not negative 2 squared, because the parentheses does not include the negative. And we couldn't do it if it was negative 2, because we learned at the beginning of class that our b value has to be greater than 0. Okay? B value has to be positive.
Now on to the fun with translations. H and K, this is just like stuff we've been doing all year. We did this with absolute value graphs, we did this with quadratic functions, we keep shifting things, square root graphs, all that stuff. When it's inside the exponent with the x, we're shifting it the opposite way of what you'd expect. So if it says a minus, then we're shifting it right. If it's here on the outside though, plus k would mean up. So we're shifting it horizontally, left and right, h units, and vertically up and down by k units. Let's do it. So here's our first one. My recommendation is to start off with what were the original points before we shift them. So 0, comma, a. A would be a 2. Okay, don't worry about this minus 1, minus 4 yet. We're going to completely ignore that stuff for just a minute. Just look at this 2 times 2.
Now he's doing it a little different way, just so you know. He's going with the original points and then doing the translations on them. Okay? If you were going the straight T-chart way, you're just plugging in numbers then. Okay?
3 raised to the x. And then we'll build the other thing. So 0, 2. And then we're going to shift that. We'll worry about the shifting in a minute. And then we have a coordinate point of 1, comma 6. A times b. And then we'll shift that. And then we have a coordinate point of 2, comma, let's see, 3 squared. We do 3 squared times, that's 9, times 2, 18. Ooh, that's a big number, 18. And we're going to shift that. All right, so now what is our new coordinate point? Let's write this in red so it stands out. So what we're doing is we're going to add 1 to the x values.
Remember thinking
Shifting
opposite.
Right, put a little plus 1 up here. Plus 1 to all these x values. And then we're going to subtract 4 from the y values because we are going down. So then we go minus 4 to the y values. So my new coordinate points now are going to be, all the x values are added 1. This one becomes a 2. This becomes a 3. Then my y values, I subtract 4 from them. So now I have 2 minus 4 is negative 2. I subtract 4 from 6, I get a positive 2. Subtract 4 from 18, and you get a 12. Now this coordinate point, this last one, that's going to be way off my graph, but that's okay. These other two can help me. So now let's do this. First thing, maybe in the side of your notes, great place to write this. When you've shifted things, my recommendation is 1, 2, 3, 4. Draw the vertical asymptote, not vertical, excuse me, this horizontal asymptote. Do that first, because the asymptote is kind of like your guide to help you know the boundary of your graph. And then we can plug in these points. So we're going to go over 1 and down negative 2. There's one of the points. And where's my next one? 2, 2. So 1, 2, 1, 2.
So why did we add 1 instead of subtracting?
Because we think oppositely when it's attached to the x. Yep, we think opposite attached to the x. Matt, because it said minus 4. So that shifts the whole graph down 4. So if it was started at y equals 0, now my asymptote gets shifted down 4, so my asymptote goes down 4 with it. Okay? Hunter, was that you too? Okay?
And then if I could go 312, it'd be way off the grid, way up here somewhere. 312. So then I have my asymptote. It's going to be going right along the asymptote, and then it curves up pretty sharp here. It's going to go really steep. And
Do that one.
it's really hard to make this straight. This electronic pin here. All right, there we go. There is my graph. Domain, easy peasy, all real numbers. That's what it always is for exponential.
Exponential functions
The
are
range
always
is different.
has domains of all real
It's
numbers.
y is greater than, because it's above the asymptote. And what's this asymptote? It was shifted down 4, so y is greater than negative 4. All right, we're done with all of the skills portion of the lesson. Let me go back and talk about real quick our poor princess, Princess Kellerina. What's going on with her, and what's happened with the money that Serafina was trying to get? So if you remember our little chessboard that we had, so how much money was there? Well, we need a formula. You don't need to write this part down. Let's just kind of watch this for a second. Here's the formula that would work with this situation. There was 1 penny that we're starting with on the first square, and we're doubling it. Now this x minus 1, don't worry too much about it, but the x represents what square number we're on. If we plug in a 1 here, that would be the first square. So we're not doubling yes, we need this to be a 0. We haven't doubled. On the second square, we're doubling. So don't worry too much about this. Here's the formula. If we then plug in 64, because there's 64 squares, we get how much money is just on the last square. So if we do this, plug in our trusty calculator, we get some crazy thing like this. 9.223 times 10 to the 16th power. How big is that? 92 with a bunch of other numbers behind it. Look how long that is. That's $92 quadrillion. That's how much is right here on the last square alone. Half of that would be here. So Urbino would have, basically he's bankrupting the entire kingdom. So he, poor King Gonzalo did not really get a good deal out of that. He thought he did. That's how fast exponential growth can make things get larger that fast. $92 quadrillion on the last square. Awesome. That's a lot of money. Alright, that's the end of our lesson. Good to be with you, teach you about exponential growth functions. This is Mr. Bean signing.
Okay. So, one more thing to talk about here then is, because it'll be in your homework tonight. Okay. At the bottom of your notes, don't be packing up yet, because I'm still talking in your note packet. Okay. You should see something along the lines of y equals a times, what is it? I forget what it is. Oh, they went p. They didn't go p. Okay. Y equals p times 1 plus r divided by n to the nt power. Right? Okay? It's what? It's a instead of y? Okay. You knew they had an a in it somewhere. Okay? What this is this is the compound interest formula. Okay? A is your amount. P is your start value. R is your rate. Okay? But remember, most of the time it's going to be in a percent. So you got to switch it into a decimal in order to use it. Okay? You got to switch it in a decimal. T is time, but that is in years. N is the number of times it's compounded per year. So if it was compounded once annually, that would be n would be 1. If it's compounded monthly, n would be 12, because there's 12 months in a year. If it's weekly, it's 52. Okay? So that's the number of times that it's compounded per year. You'll need that for your homework this evening.